Hello everyone, and welcome. I'm excited to kick off today's presentation on the fascinating topic of the atomic nucleus. Today, we'll explore what makes up the core of an atom and understand its significance in the world of science. We'll cover the basic structure, the particles involved, and why the atomic nucleus is so important. So, let's get started and delve into this intriguing subject together. Let's start by looking at the foundational concepts that led to our current understanding of nuclear processes. First, we'll explore radioactivity and Soddy's displacement law. This law is crucial because it explains how elements change when they emit radiation, helping us understand the stability of different nuclei. Soddy's work showed us how elements transform into other elements through radioactive decay, which is a key idea in nuclear science. Next, we'll move on to Rutherford's alpha scattering experiment. This experiment was groundbreaking because it revealed the structure of the atom. Rutherford's team shot alpha particles at a thin gold foil and observed how they scattered. The unexpected deflections led to the discovery of a small, dense nucleus at the center of the atom. Finally, these discoveries set the stage for understanding nuclear fission and fusion. These processes involve splitting or combining atomic nuclei, releasing enormous amounts of energy. They are the basis of nuclear power and atomic weapons. So, by understanding radioactivity, the atom's structure, and the behavior of nuclear particles, we gain insight into the powerful nuclear reactions that shape our world today. Let's take a closer look at Rutherford's alpha scattering experiment. This experiment was a pivotal moment in understanding atomic structure. Rutherford aimed a beam of alpha particles, which are essentially helium nuclei, at a very thin sheet of gold foil. The goal was to observe how these particles interacted with the atoms in the foil. Most of the alpha particles passed straight through, which was expected if atoms were just tiny, indivisible particles. However, some particles were deflected at large angles, and a few even bounced straight back. This was a surprising result at the time and suggested that atoms weren't just solid spheres. Instead, Rutherford proposed that atoms have a small, dense, positively charged core, what we now call the nucleus. This experiment was crucial because it shifted our understanding of atomic structure and laid the foundation for the nuclear model of the atom. It's a perfect example of how carefully designed experiments can challenge existing ideas and lead to new scientific breakthroughs. When we consider the situation where the distance between the alpha particle and the nucleus is exactly equal to the distance of the closest approach, which we denote as R0, something interesting happens. At this specific point, the alpha particle essentially comes to a stop. This is because all of its initial kinetic energy has been transformed into electric potential energy of the system. This concept is crucial because it highlights the interplay between energy forms, kinetic energy converting into potential energy during the interaction. The distance of closest approach, or R0, is significant because it gives us a measure of how close the alpha particle can get to the nucleus before it stops, indicating the strength of the electrostatic forces involved. It's also important to note that this distance of closest approach is often comparable to the size of the nucleus itself, which we refer to as the nuclear size. This connection helps us understand the scale at which nuclear interactions happen and provides insight into the structure of the nucleus. Overall, this point ties into our broader theme of understanding atomic interactions and the energetic exchanges that occur during nuclear collisions. Recognizing how kinetic energy is completely converted into potential energy at this specific distance helps us grasp the fundamental nature of nuclear forces and particle behavior. Let's look at how the impact parameter influences the scattering of alpha particles. First, consider the case where B equals 0, meaning the alpha particles are directed straight towards the center of the nucleus. In this scenario, the scattering angle theta is either 0 or 180 degrees, corresponding to cotangent of theta/2 being 0 or infinite. Essentially, the particles retrace their paths after hitting the nucleus, indicating a head-on collision. Next, if the impact parameter is small but not 0, cotangent of theta/2 becomes small, which means the scattering angle theta is large. So, alpha particles traveling close to the nucleus experience significant deflections, deviating sharply from their original paths. Conversely, when the impact parameter is large, cotangent of theta/2 is large, and the scattering angle theta is small. This tells us that alpha particles passing far from the nucleus undergo only minor deflections, maintaining much of their initial trajectory. Now, the impact parameter itself is defined as the perpendicular distance between the initial velocity vector of the alpha particle and the center of the nucleus when the particle is still far away. Think of it as the closest approach path the particle would take if there were no forces acting on it. Understanding the impact parameter helps us grasp how the initial conditions influence the scattering behavior and, ultimately, the structure of the nucleus. It's a key concept connecting the particle's trajectory to the nuclear forces at play. Now, let's talk about the fundamental particles that make up the nucleus. First, we have the neutron. It's a particle with no electric charge, so it's neutral, and its mass is approximately 1.675 times 10 to the minus 27 kilograms. To give you a sense of scale, that's about 1840 times heavier than an electron. These neutrons play a crucial role in stabilizing the nucleus, especially since they don't carry a charge that would cause repulsion among protons. Next, we have the proton. Unlike neutrons, protons carry a positive charge of roughly 1.6 times 10 to the minus 19 coulombs and have a similar mass to neutrons, about 1.67 times 10 to the minus 27 kilograms. Interestingly, protons are about 1836 times heavier than electrons. When we look at the composition of an atomic nucleus, it's important to note that almost every nucleus, except for hydrogen, contains both protons and neutrons. Hydrogen's nucleus is unique because it contains only a single proton. This combination of protons and neutrons defines the identity and stability of the nucleus, which ties back to the overall theme of understanding atomic structure. Let's start with the atomic mass unit, or AMU. The AMU is defined as 1/12 of the mass of a single carbon atom. To put that into perspective, it's approximately 1.66 times 10 to the negative 27th kilograms. This unit helps us compare atomic masses more conveniently instead of dealing with very tiny numbers. Moving on, the atomic mass number, often denoted as A, is simply the total number of protons plus neutrons in an atom's nucleus. Think of it as the sum of the particles that give an atom its mass. So, if you know the number of protons and neutrons, you can find the atomic mass number by adding them together. And then there's the atomic number, Z, which is just the number of protons in the nucleus. It's fundamental because it defines the element itself. For example, all carbon atoms have 6 protons, so their atomic number is 6. These three concepts, atomic number, atomic mass number, and atomic mass unit, are key to understanding the structure of atoms and how we measure and compare different elements. They form the foundation of atomic theory and help us grasp the building blocks of matter. Let's talk about nuclear density first. The density, represented by ρ, is calculated as mass divided by volume, and for nuclei, it's approximately 2.29 times 10 to the 17 kilograms per cubic meter. This tells us that nuclear matter is incredibly dense, much more than everyday materials. Next, the mass of a nucleus depends on its mass number A, since one atomic mass unit, or AMU, equals about 1.66 times 10 to the minus 27 kilograms. We multiply A by this value to find the nucleus's mass in kilograms. So, a nucleus's mass scales directly with its number of protons and neutrons. Moving on to volume, we use the formula for the volume of a sphere, which is 4/3 pi times radius cubed. But since the radius depends on A, we express it as r equals r0 times A to the 1/3 power, where r0 is a constant, approximately 1.2 femtometers. This means as the nucleus gets larger, its radius increases proportionally to the cube root of its mass number. It's important to note that the nucleus doesn't have a sharply defined boundary. Instead, its surface is somewhat fuzzy. Still, We can approximate its radius using that r equals r0, a 1/3 relation. Typical radii range from about 1 femtometer for light nuclei up to around 10 femtometers for heavier ones. In summary, understanding the radius and volume helps us see why nuclear matter is so densely packed. The constant density across different nuclei indicates that, regardless of size, nuclear matter maintains a remarkably uniform density, which ties into the overall theme of nuclear structure and stability. Let's talk about the concept of mass defect. It is the difference between the rest mass of a nucleus and the total mass of the individual nucleons that make it up. Essentially, when these protons and neutrons come together to form a nucleus, the combined mass is actually less than the sum of their separate masses. This missing mass, or mass defect, is quite significant because it relates directly to the energy that holds the nucleus together. Now, to understand why this happens, we need to consider Einstein's famous mass-energy relation. It tells us that mass and energy are interchangeable. In fact, the mass defect corresponds to a release of energy, which is what binds the nucleus. This is a key idea because it links the concepts of mass and energy, showing how nuclear binding energy is stored within the nucleus. And this ties back to our overall theme of understanding atomic structure and the forces at play. The mass defect isn't just a curious fact. It's a window into how energy and matter interact at a fundamental level, explaining why nuclear reactions release such vast amounts of energy. Now, let's take a look at what we mean by binding energy per nucleon. Essentially, it's the total binding energy of a nucleus divided by the number of nucleons, or protons and neutrons, that it contains. This value gives us a good sense of how tightly bound each nucleon is within the nucleus. When we talk about binding energy, we're referring to the energy needed to break apart a nucleus into its individual protons and neutrons, and then to move those particles infinitely far apart. In other words, it's the energy required to completely disassemble the nucleus. Mathematically, we express this as BE equals the change in mass times the speed of light squared, or deltum C2. This relates mass defect directly to energy, highlighting Einstein's famous equation. So, by examining the binding energy and the binding energy per nucleon, we gain insight into the stability of different nuclei. Nuclei with higher binding energies per nucleon are generally more stable. This concept connects to the broader theme of nuclear stability and energy release in nuclear reactions. Understanding these ideas helps us grasp why certain isotopes are more common or more stable than others, and how nuclear energy can be harnessed. Let's take a closer look at the binding energy per nucleon for very light nuclides. Initially, you'll notice that this value is quite small, which means these nuclei are not very stable. However, as we move to slightly heavier nuclei, there is a rapid increase in the binding energy per nucleon. This rise indicates that the nuclei become more stable as they gain more nucleons. The key point here is that the maximum binding energy per nucleon is reached around mass number 56, which corresponds to elements like iron and nickel. This peak signifies the most stable nuclei in nature. Understanding this curve helps us infer how nuclear stability varies with size and is fundamental to concepts like fusion and fission processes that power stars and nuclear reactors. So, in summary, the binding energy curve not only shows us the stability of different nuclei, but also connects deeply to the processes that shape our universe. Now, let's talk about the forces that exist between protons and neutrons inside the nucleus. These forces are what hold the nucleus together, despite the repulsive electrical forces between positively charged protons. They are known as nuclear forces. These nuclear forces can be explained through what's called meson theory. Essentially, mesons act as the particles that mediate or carry these forces between nucleons, which are protons and neutrons. There are three main types of mesons involved here. The first is the positive meson, known as pi plus or pi plus. Then there's the negative meson, pi minus or pi. And finally, we have the neutral meson, pi 0 or pi 0. Understanding these mesons is key because they help explain how protons and neutrons attract each other within the nucleus, ensuring its stability. This concept is a fundamental piece of nuclear physics and ties back to our overall theme of understanding atomic structure and forces. Let's take a closer look at radioactivity and Soddy's displacement law. Radioactivity, as you know, is the process by which unstable atomic nuclei release energy to become more stable. This process is spontaneous and involves the emission of particles or radiation. Now, Soddy's displacement law is a key concept here. It helps us understand how the elements transform during radioactive decay. Essentially, it states that when a radioactive element decays, the new element formed is displaced by one place in the periodic table compared to the original. This helps us predict the changes in atomic number and mass number during decay. Recognizing this pattern was crucial in understanding the decay series and the nature of radioactive transformations. So, in the context of our overall theme, grasping this law gives us insight into the fundamental behavior of radioactive materials and how elements evolve over time through decay. Let's now look at some important units used to measure radioactivity. First, we have the becquerel, abbreviated as BQ. 1 becquerel represents the activity of a radioactive substance if it undergoes just 1 disintegration per second. It's a straightforward way to quantify how active a sample is. Next is the curie, or CI. This unit is much larger. 1 curie corresponds to 3.7 times 10 to the power of 10 disintegrations per second. It was historically used more in the past, but is still important for understanding larger quantities or older measurements. Moving on to the concept of half-life. This is a key idea. It's the time it takes for half of the radioactive atoms in a sample to decay. If we denote the number of radioactive atoms at any instant as n, then the rate at which these atoms decay is proportional to n itself, expressed mathematically as dn/dt equals minus lambda times, and rearranging this differential equation gives us the exponential decay law. N equals n0 times e to the power of minus lambda t. Now, talking about disintegration, it's important to remember that radioactive decay is a completely random process. The rate of decay doesn't depend on the physical or chemical state of the material. It's an inherent property of the nucleus itself. Radioactivity, as a phenomenon, involves the spontaneous emission of alpha, beta, and gamma radiations from unstable nuclei. Finally, Rutherford and Soddy established some fundamental laws of radioactive decay. These laws help us understand how radioactive substances transform over time. And related to this, Soddy's displacement law describes how the decay of one element leads to the formation of another, often changing the chemical properties of the material as it progresses through different decay stages. Let's take a closer look at nuclear fission and fusion. These are 2 fundamental processes that release energy from atomic nuclei, but they do so in very different ways. Nuclear fission occurs when a heavy nucleus, like uranium or plutonium, splits into smaller nuclei, releasing a significant amount of energy. This process is the principle behind most nuclear power plants today. It's efficient and produces a lot of energy from a relatively small amount of fuel, but it also creates radioactive waste that we need to manage carefully. On the other hand, nuclear fusion is the process that powers the sun. It involves light nuclei, such as hydrogen isotopes, merging or fusing together to form a heavier nucleus. Fusion releases even more energy than fission and produces fewer radioactive byproducts. However, achieving controlled fusion on Earth is incredibly challenging and remains a goal for future energy sources. Both processes are key to understanding how we can harness nuclear reactions for sustainable energy. Fission is already in use, but fusion holds the promise of a cleaner, more abundant energy source in the future. Connecting these concepts to our overall theme, they illustrate the incredible potential of nuclear science in shaping our energy landscape. Let's take a closer look at nuclear fusion. Essentially, nuclear fusion is a process where 2 lighter nuclei come together to form a heavier nucleus. This merging releases a tremendous amount of energy, which is why it's such an exciting potential source of power. Think of it like the process that powers the sun and other stars, where hydrogen nuclei fuse to create helium and release energy. Now, moving on to chain reactions. For a chain reaction to happen in nuclear fission, the material needs to be above a certain size known as the critical size. If it's smaller, the neutrons escape and the reaction stops. But when the material is larger than this critical size, the neutrons produced in one reaction cause more nuclei to split, creating a self-sustaining process. This is key to how nuclear reactors and weapons work. Speaking of nuclear fission, this process involves a heavy nucleus splitting into two smaller, yet comparable, nuclei. This splitting releases a huge amount of energy, much like in nuclear power plants or bombs. The energy released from both fission and fusion processes is what we harness for power, which ties back to our overall theme of understanding nuclear reactions and their potential. So, in summary, both nuclear fission and fusion are fundamental nuclear reactions, each with unique mechanisms and energy outputs. Understanding these processes helps us explore their applications, especially in the pursuit of clean and sustainable energy sources. Let's take a closer look at the proton-proton cycle, which is the primary energy source for the Sun. This process begins with two protons, or hydrogen nuclei, fusing together to form a deuteron, a positron, and a neutrino, releasing about 0.4 MeV of energy. This step is crucial because it marks the start of the chain reaction that powers our star. Next, this deuteron combines with another proton to create a helium-3 nucleus, releasing around 5.5 MeV when two helium-3 nuclei meet. They fuse to produce a helium-4 nucleus, releasing 12.9 MeV of energy, along with two protons that can then participate in the cycle again. This entire process is what we call nuclear fusion, and it's the fundamental mechanism that converts hydrogen into helium, releasing vast amounts of energy. This energy radiates outward, ultimately reaching us as sunlight. So, understanding this cycle helps us grasp how stars generate the energy that sustains life on Earth. It's a perfect example of how nuclear physics connects to the bigger picture of our universe. All right, let's take a look at the end of the atomic nucleus and what it signifies in stellar processes. On the slide, we see a series of nuclear reactions involving carbon and nitrogen isotopes. For example, one reaction shows a carbon-6 nucleus combining with a proton to form nitrogen-7 plus gamma radiation. This illustrates how nuclei can fuse and release energy, which is fundamental to how stars generate power. Another reaction involves nitrogen-7 undergoing positron emission, transforming back into carbon-6 and releasing energy again. These processes are part of a cycle, specifically the carbon-nitrogen cycle, which is a key pathway for energy production in stars that are similar to our Sun. This cycle essentially acts as a stellar engine, converting hydrogen into helium, with carbon and nitrogen acting as catalysts. Connecting this to the overall theme, these nuclear reactions illustrate how stars harness nuclear fusion to produce energy. Fusion is the core process that powers stars, allowing them to shine and evolve over millions to billions of years. So, understanding these reactions helps us grasp the fundamental mechanisms behind stellar energy sources and how elements like carbon and nitrogen play vital roles in this cosmic process.